Okay, so in this problem we have a square block of mass m, which strikes a small step at O while traveling to the left with a speed of v. And based on this information, we're asked to determine the value of v required for the block to just reach a standing position with zero velocity after impact, assuming it sticks to the step. So I think the key thing to note here is that if we're going to assume this thing sticks to the step once it impacts it, it's almost like treating O as a fixed point. In this regard, we can draw a free body diagram for this system in arbitrary orientation. And note that what we're going to have here is a force due to weight, so we'll have mg, and we'll have some reactions here at O, which I can call OX and OI respectively. Now the further thing I can note here is that if we look at essentially the instant when the sticking or the impact occurs, what we're going to have is essentially no change in mg, and so in other words mg is not going to provide an impulsive moment. And so thus what we can say in this case is if we treat 1 an instant before impact and 2 the instant immediately after impact where we just slightly start to rotate about 0.2, what I can say is that h about O at state 1 is equal to h about O at state 2. Perhaps the clarity here that is lost is that mg is not going to contribute a moment not so much because the force doesn't exist, but because the time interval of which this interaction would take place would be comparatively small. So once I have this here, what I can say is that h about O at state 1, this thing is initially translating, and so we can treat this almost as like a particle. And so what we can do here is we can say this is going to be R1 cross mv1, where of course R describes the position vector to point G from O, so in this case this is going to be A over 2 in the I plus A over 2 in the J, where I use conventional I, J coordinates, and I'll cross that with the mass of the block m times its initial speed, which is minus v1 in the I direction. So if I go ahead and expand this out here, I cross I goes away, j cross I gives me minus k, minus a minus is a plus, so I'm going to have here m times v times a divided by 2 in the k direction. Now with the second case, immediately post-impact, it's behaving like a rigid body rotating about point O, and so I can say that this then is going to equal I about O times omega 2 in the k direction. In this case, I can note that I about O is going to equal I about G of the block plus m times the distance between O and G squared, and that's going to be times omega 2 in the k. I for a nice square block like this is going to be given by 1/12 times the mass of the block times the width squared plus the height squared, and I'm going to add to that m times the distance between O and G, which is essentially this hypotenuse squared. So if this is A and this is A, this is going to be root 2a, and so if I square that, I'm going to simply have times 2a squared. All of this will be times omega 2 in the k. Now if I go ahead and equate h about O at state 1 and h about O at state 2, what I realize is I can get back from this essentially omega 2 as the function of the initial speed v1. Now why is this useful? Because if I have 2, I can start moving towards what I'll call a state 3, which is where the block just reaches the standing position. If we just reach the standing position, what we'll note is that's going to be the position where the center of mass G is immediately above O. So if we call this position 3, we can now use work energy between points 2 and states 2 and states 3 to get the final answer. So in this regard, I'm going to say T2 plus V2 is plus the non-conservative work done in moving between states 2 and state 3 is going to equal T3 plus V3. Initially, we're in a state of pure rotation about O, so I'll have a kinetic energy of 1/2 I about O times omega 2 squared. I can go ahead and choose to put my datum at the ground level, and should I do that then, V2 is going to be plus m times G times A over 2. Note that there's no forces which contribute non-conservative work here. T3, that point where we're at the maximum height, is going to be 0. And then V3, we're going to have m times G times the distance between the center of mass and O, which we call DOG, and now we have our result. Because we know in this case DOG is equal to root 2 times A, I can substitute that result in here, and I can get the critical value for omega 2 required to get standing position, and if I plug that back in to this equation up above, I can find the critical value of V1, which gives me the answer. So from here on out, this is a straightforward exercise in substitution, and one which I know you can handle. So let me simply wish you the best of luck. Take care, everyone.